The U.S. Army Corps of Engineers made a billion-dollar bet, and if they lose, hundreds of thousands of people could drown. Right now, one of the largest dams in the United States is holding back over 1 trillion gallons of water. It is a monument of concrete and steel, a 40-story wall standing between a massive reservoir and the towns, farms, and cities that lie sleeping in the valley below. But that wall has a secret. For decades, it has been leaking, dissolving from the inside out. An army of engineers spent years and over $1 billion on a desperate repair they believed had saved it. It should have been the final fix. It should have ended the story. But here's what they didn't tell you. The foundation is still shifting, the water pressure is finding new ways through, and a new crack has just appeared. Not in the ground beneath the dam, but in the concrete heart of the structure itself. So the real question is, did they just perform one of the greatest engineering saves in modern history, or did they just place a band-aid on a catastrophe that is already in motion? Most people who watch our channel to the end aren't subscribed. If you value this kind of deep dive investigation, click that button now. It's the single best way to make sure you don't miss the next urgent story, and it's the most important way you can support this work. You won't regret it. Now let's begin. Wolf Creek Dam was never supposed to be vulnerable. It was born in an era of American certainty, a time when the nation believed it could conquer any landscape with enough concrete and ambition. Authorized in 1938 and completed in 1951, it was part of a wave of massive public works projects designed to tame the country's wild rivers, providing flood control, hydroelectric power, and economic lifeblood to entire regions. The dam stretches for over a mile across the Cumberland River in southern Kentucky. It is an immense structure, a combination of a sprawling earthen embankment and a towering concrete gravity dam. When its gates closed for the first time, it created Lake Cumberland, a reservoir so vast it holds more water than the next 2 largest lakes in the state combined. The statistics are staggering. The lake has over 1,200 miles of shoreline. Its waters could cover the entire state of Delaware 2 feet deep. Downstream, the city of Nashville, Tennessee, diners and dozens of smaller communities rely on the dam to shield them from the devastating floods that once ravaged the Cumberland River Valley. The dam was a promise written in concrete. It was a symbol of security, a permanent solution, and it was built on a lie. The engineers who selected the site in the 1940s knew what they were building on. The ground here is made of karst, a specific type of geology famous for its instability. Karst terrain is formed from the dissolution of soluble rocks, primarily limestone. Over thousands of years, water seeps through the ground, slowly dissolving the rock and creating a hidden subterranean world of caves, voids, and conduits. It is a landscape that is hollow from the inside. To an engineer, it's like building a skyscraper on a foundation of Swiss cheese. They knew the risks. They believed they could engineer their way around them. During construction, they implemented what was, for the time, a state-of-the-art solution. They drilled a series of deep holes into the limestone bedrock beneath the dam's planned footprint and pumped in thousands of tons of a concrete mixture called grout. This created what is known as a grout curtain, a supposedly impermeable barrier deep underground designed to block those hidden pathways and prevent water from seeping under the dam. It was an audacious plan, an attempt to seal an entire landscape. And for a while, it seemed to work. The lake filled, the turbines spun, the valley below was safe. The promise was kept. For 16 years. Then, in 1968, the lie began to reveal itself. Maintenance crews walking the base of the dam noticed something unsettling. Muddy water was bubbling up from the ground downstream. Not just seepage, which can be normal, but water carrying sediment, silt, clay, the very material that the dam's earthen embankment was made of. The implications were chilling. Water from the immense pressure of the lake was not just finding a way through the limestone bedrock. It was finding a way through their grout curtain, and it was now powerful enough to be eroding the foundation from underneath the dam itself, carrying microscopic pieces of the structure away with every gallon that escaped. The dam was dissolving. Slowly, invisibly, from the bottom up. The Army Corps of Engineers, the agency responsible for the dam, immediately understood the gravity of the threat. This wasn't a leak you could patch. This was a fundamental failure of the geology the entire monument was built upon. The problem was not the concrete, it was the continent. What would you do if you lived downstream from a structure like this, knowing that the very ground it stands on is slowly disappearing? Let us know in the comments. The internal alarm bells were now deafening. An uncontrolled failure at Wolf Creek Dam would be an event of almost unimaginable destruction. A wall of water nearly 200 feet high would obliterate everything in the river valley for dozens of miles. Small towns like Burkesville and Salina would be erased from the map in under an hour. Further downstream, the flood crest would reach Nashville, a major American city, in less than a day, overwhelming its own flood defenses and causing catastrophic damage. The potential loss of life was measured in the tens, if not hundreds, of thousands. The economic damage would run into the tens of billions. This was not a theoretical risk. It was a mathematical certainty if the erosion continued unchecked. So began one the longest, most expensive, and most desperate repair efforts in American history. A silent, high-stakes war waged hundreds of feet below the surface against geology and time. The first phase, started in the late 1960s, was an aggressive expansion of the original idea. More grout. Engineers drilled thousands of new holes, deeper and closer together this time, and pumped in a new, more advanced chemical grout mixture. For 10 years, drilling rigs were a permanent feature at the dam. It was a brute force approach. I can attempt to plug every last void and fissure in the dissolving limestone foundation. The work was difficult, expensive, and ultimately a temporary fix. They were plugging holes in a system that was actively creating new ones. The water was relentless. It simply found new, weaker paths through the karst. The muddy seepage slowed, but it never stopped. The dam was still leaking. The foundation was still eroding. The catastrophe was still waiting. By the early 2000s, the situation had become critical. New monitoring instruments inside the dam showed that the rate of erosion was accelerating. The risk of a sudden failure was now deemed unacceptable. The Army Corps of Engineers made a drastic decision. They lowered the level of Lake Cumberland by more than 40 feet. Sacrificing immense hydroelectric revenue and devastating the local tourism economy, all to reduce the pressure on the dam's failing foundation. It was a public admission that the largest dam in the region was no longer safe at its full capacity, and it bought them time to attempt the impossible. The plan they devised was something out of science fiction. The grout curtains had failed. Simply pumping in more concrete was like trying to fill the ocean with a bucket. They needed a permanent solution, a physical barrier, so they decided to build a wall. Not in front of the dam or behind it, but through it. Directly through the center of the earthen embankment, extending hundreds of feet down into the bedrock itself. It would be a solid, continuous wall of concrete over a mile long and nearly 300 feet deep. A permanent cutoff designed to block any possible path for water to get through. It was called the cutoff wall, and it had never been attempted on this scale, on a dam this large with a problem this severe. The cost estimate was breathtaking. Nearly $600 million. If you know anyone who lives near a major dam or who is fascinated by these massive engineering challenges, share this video. The story of what happened next is something they need to see. And if you're getting value from this deep analysis, take a second to hit the like button. It tells our team that these investigations are making an impact. Construction of the cutoff wall began in 2007. It was less a construction project and more a form of industrial surgery. The challenge was immense. How do you build a solid concrete wall inside a fragile earthen dam that is actively leaking without causing the very collapse you're trying to prevent? The solution was a specialized piece of equipment called a hydromill. Imagine a giant remote-controlled cutting tool suspended from a crane that grinds a narrow trench deep into the earth. As the hydromill dug down, layer by layer, the trench was kept filled with a thick, heavy slurry made of bentonite clay. This slurry was dense enough to hold the walls of the newly cut trench open and prevent the surrounding earth from collapsing inward. Once a section of the trench was excavated to its full depth, reaching solid, unweathered bedrock far below the leaky karst, a massive, prefabricated steel-reinforced concrete panel was lowered into the slurry-filled void. Meet panel by panel, section by section, they slowly built a fortress inside the dam. Each panel had to interlock perfectly with the next, forming a seamless, watertight barrier. The precision required was extraordinary. The alignment had to be perfect over a distance of more than 4,000 feet, all of it happening hundreds of feet underground, completely blind. The work was agonizingly slow. For 6 years, the crews worked 24 hours a day, 7 days a week. The cost inevitably spiraled. The initial $600 million budget swelled. Unexpectedly complex geology required new techniques. Equipment broke down. The sheer difficulty of the task exceeded the initial projections. By the time the final panel was placed in 2013, the total cost of the cutoff wall had climbed to over $750 million. When added to the decades of previous repair attempts, The total investment to save Wolf Creek Dam pushed past $1 billion. $1 billion to fix a single fundamental mistake made half a century earlier. In 2014, the Army Corps of Engineers declared victory. The cutoff wall was complete. The seepage had slowed to a negligible trickle. They began the slow process of refilling Lake Cumberland to its historic levels. The dam, they announced, was finally safe. The billion-dollar gamble had paid off. But geology does not surrender so easily. And here is what was happening in the darkness, deep under the weight of a refilling lake. The water, blocked by the new impenetrable wall, did not simply stop. It began to push sideways. The immense pressure of the reservoir was now being redirected, and we saw seeking new escape routes around the edges of the cutoff wall. The problem had not been solved. It had been moved. Inside the cores, a new, even more disturbing debate was beginning to take shape. The cutoff wall was a masterpiece of engineering, but it was also a rigid, unyielding structure placed inside a flexible, aging earthen dam built on top of a shifting, dissolving foundation. They had introduced a massive new variable into an already unstable equation. And then the call came. During a routine underwater inspection in recent years, a remote-operated vehicle scanning the concrete face of the dam, the part that holds back the lake, found something new. A crack. It was small. Hairline. Located on the upstream face of one of the concrete monoliths near the powerhouse. But it wasn't a surface blemish. Sonar analysis suggested it might extend deeper into the concrete mass. This was an entirely different kind of threat. The foundation was the known enemy. This was something else. Was it a result of the immense stress of the repair work? Was it a sign that the concrete, now over 70 years old, was beginning to show its age? Or worse, was it a symptom of the new pressure dynamics created by the cutoff wall, an indication that the entire structure was now being torqued and stressed in ways the original designers had never conceived? I know we mentioned this before, but if you're still here, you are clearly invested in this story. A lot of people watch this far and then get distracted. Don't let that be you. Take the 2 seconds it takes to hit the subscribe button. It is that important. You need to know what happens next in stories like this one. I promise I won't ask again. Maybe. The appearance of a structural crack, however small, changed the entire risk profile. The old problem was a plumbing issue, a leak in the basement. The new problem was a crack in the load-bearing walls of the house itself. Engineers from the Corps insist the crack is being monitored and currently poses no immediate danger. But inside the world of dam safety, there are no small problems. Concrete dams are designed to be monolithic. They rely on their immense, unified weight to hold back the force of the water. Cracks can allow water to penetrate deep inside the structure, where it can freeze and expand in the winter, a process called ice jacking that can slowly wedge the structure apart from within. Or, the pressure of the water itself can exploit the crack, a phenomenon that can lead to a progressive, accelerating failure. The billion-dollar wall had stopped the leak through the foundation. It did absolutely nothing to address the aging of the dam's primary concrete structure. The dam that was never supposed to be vulnerable was now fighting a war on two fronts. An invisible enemy below, in the dissolving karst, and a visible enemy within, etched into its own concrete face. The situation at Wolf Creek is a terrifyingly perfect microcosm of a much larger, national crisis that almost no one is talking about. The United States has over 90,000 dams. The average age of those dams is nearly 60 years old. Many of them, like Wolf Creek, were built during the mid-20th century boom, designed with a 50-year operational lifespan. Where thousands are now operating well beyond their intended expiration date. The American Society of Civil Engineers gives the nation's dams a grade of D in its infrastructure report card. There are more than 15,000 dams in the U.S. classified as high hazard potential, meaning a failure would likely cause loss of human life. Wolf Creek is just one, but its story is a warning. The engineering marvels of the post-war era are now aging relics. The concrete is getting brittle, the steel is rusting, the foundations are deteriorating, and they are all facing a threat the original designers could never have fully anticipated: a rapidly changing climate. Weather patterns are becoming more extreme. The 100-year flood that these dams were designed to contain is now happening once a decade. The probable maximum flood, the absolute worst-case scenario storm, is being recalculated by hydrologists to be larger and more frequent than previously thought. These older dams are being subjected to forces they were never built to withstand. In 2017, the crisis at California's Oroville Dam provided a stunning preview. After historic rainfall, the dam's main spillway, the concrete chute designed to release excess water safely, began to disintegrate under the immense flow. Chunks of concrete the size of cars were torn away, threatening a total failure of the spillway that could have led to an uncontrolled release of water and a catastrophic flood. Nearly 200,000 people downstream were evacuated. A disaster was averted by inches and hours. Oroville, like Wolf Creek, was seen as a titan of modern engineering, and it nearly failed. The issue is compounded by a crisis of oversight. The responsibility for inspecting and maintaining these dams is split between federal, state, and private owners. Funding is chronically short. Many states have only a handful of inspectors responsible for thousands of dams. Problems are often not found until they become emergencies. Leaks, cracks, and signs of erosion go undetected for years, quietly worsening until a major flood event suddenly turns a manageable problem into an imminent disaster. The $1 billion spent on Wolf Creek Dam is an exception. Most high-hazard dams don't have the backing of the Army Corps of Engineers. They are owned by small towns, utility districts, or private companies that simply do not have the resources to fund $100 million repairs. So they do what they can. They patch, they pray. And they lower the water levels. They manage the decline. Okay, last time. I see you. You made it all the way to the end. You're one of us, a person who needs to understand the full story. Do the thing. Hit the button. You know you want to. It's the only way to guarantee you're in the loop for the next report. So where does that leave the people living in the shadow of Wolf Creek Dam? They are protected by a $1 billion wall built inside a 70-year-old dam sitting on top of a dissolving rock foundation that is now showing new cracks in its concrete face. The engineers are confident. The monitoring is constant. The risk, they say, is managed, but the laws of physics are unforgiving. Water will always seek the path of least resistance. Concrete will always age. And the ground beneath our greatest achievements is not always as solid as it appears. Wolf Creek Dam is not a failure, not yet. It is a testament to the sheer, stubborn ingenuity of engineers who refuse to let it fail. The cutoff wall is real. The monitoring systems are real. The dam still stands, holding back 1 trillion gallons, protecting hundreds of thousands of lives. That is extraordinary. But it is also not a permanent guarantee. It is a truce with geology. The $1 billion repair did not defeat the fundamental problem. It only bought time. Time for the concrete to age. Time for the climate to change. Time for the water to find another way. Whether that time is measured in years or decades or generations is not an engineering question. It is a geological one. And deep beneath the surface of the lake, in the silent, hidden world of the karst, the clock is still running.